This is what we plan to do today. Okay. So now, without further ado, let us remind ourselves what groups are. What is a group? A group is a collection of elements. So you can call them anything, right? You can call them like Orgo, Vibhav, Dola, that kind of thing, Mehak, or we can call them ABC, etc. For now, since we don't want to write too much, we will write ABC. And one thing don't forget is order of a group is the total number of elements that are there. Okay. Now, let us relate this to our problem of symmetry. If you believe for a moment that the symmetry operations of a point group actually form a group, then what will be H for that point group? What is H? What is the order for a point group? You are playing a spoil sport. I am asking a simpler question. What is H? H is just the total number of symmetry operations. But the reason why I state what seems to be the obvious is that people confuse between operations and elements. Please don't do that. H, the order of the point group, is the total number of symmetry operations, not the total number of symmetry elements. Okay. For example, in C3V, how many symmetry elements are there? C3V, ammonia. I will tell you one, E, C3, then elements, the 3 sigma V's, 5, 2 plus 3 is 5, not 4, definitely, right. So, 5, but H is not 5. What is H? E, C3, then C3 square. C3 square is a different symmetry operation, don't forget that. Then sigma V, sigma V, sigma V, 6. So, H is going to be 6. Okay. Please don't forget that. When we talk about order in terms of in the context of symmetry point groups, we are talking about the total number of symmetry operations, not element. Okay. So, a collection of elements, but not just any collection of elements, a collection of elements that behave in a particular way, and a collection of elements which have certain properties. What are the properties of elements of a group? What are the properties of group? Reciprocity, then yeah, associativity, right, identity, yeah, of course, then closure, and generally I like to start with closure. Right. What happened? Oops. Closure means that whatever the operations are there, right, if you take their products means you operate, well, I am talking in terms of group right now, not symmetry operation, but to come to that also. If you take the products of the elements of a group, say AB or BA or A square, then all these should also belong to the group. That is closure. Okay. If I now think in terms of a symmetry point group, let us say C3V once again. In terms of C3V, what is the meaning of product? What are the operations? Tell me again. C3 and let us say sigma V. So, if I write, so like AB, if I write C3 dot sigma V, what does that mean? I have something, say phi, right? I make C3 operate on phi, and then I make sigma V operate on whatever is the transformed coordinate. So, this is what I write as sigma v C3 phi. Okay. So, what I am saying is that you have E, you have C3 square, then sigma v, I will call it A, sigma v B, sigma v C. Okay. So, if something if there is a function on which sigma v A operates and then C3 operates and then sigma v operates on it, then what I get should also be a member of the group. Let us see. Okay, it is not a bad idea to write like this, because then sigma v A, sigma v B, sigma v C can be assigned very easily, isn't it? Of course, when I have written A, B and C, I mean H A, H B, H C, do not get confused there. They are the same thing, just that I want to write it like this. So, when C3 operates on it, what do I get? Let us say like this. Where will A go? B. Where will your B go? Oops, sorry. A, B, C. Now, let us say we operate sigma C, or rather sigma A. What was the original sigma A? What was the original sigma A? The plane of the paper. Then what do I get? N, C, B, A. What is that? Can I go from here to here by a single symmetry operation? Sigma VB, right? So, what I get then is sigma V, which one did I operate? A C3 is equivalent to sigma V B. Original molecule. Okay. All right. So, what you can do is, whenever you have the time and inclination, you can work out this thing for each and every element, each and every product. Okay. And you will find that whatever you get is another symmetry operation of C3V. Doubt? Question? Yeah, we have been deceived actually. What was the original position? No. No. So, that is what I said. When we designate the planes, we have to stick to the original nomenclature. So, we have to behave as if the planes are space fixed. Okay. Sigma C dashed. Fine. Okay. You can work it out. You see that you will be able to draw something like this. C3V E C3 square. In fact, I will write sigma A, sigma B, sigma C. Okay. Now, let me write it here as well. E C3 square, sigma A, sigma B, sigma C. Alright. So, how do I write this element? This is EE. Which E first? This first, this second. This one first, this one second. What is E dot E? E. What is the next one? Actually, it's EC3. C3 operates first, right? Then E operates afterwards. That's how we write it, right? So this is C3, and I think by now you'll not disagree with me if I go ahead and write this. Okay, and similarly, I think you understand how to write the first column. And then what you can do is you can fill in the rest. Try doing it. You will find out that for each of these elements, you will be able to write one of these. For example, what is C3 C3 square? E. What is C3 square C3? E. What is sigma A sigma A? Sure? Yeah. Sigma B sigma B, sigma C E. Huh? So I worked out so many, now you work out the rest. I worked out all the difficult ones. Work it out, you will see that you will be able to write something, one among these. We have already demonstrated one. So please try this out yourself and convince yourself that at least for C3b, the property of closure is satisfied by the set of symmetry operations. First property is closure. Okay, we understood closure and we have convinced ourselves that for C3b, the set of symmetry operations satisfy the property of closure. Okay. Next one is the presence of an identity element. Ex equal to xc equal to x. An identity element is such that it multiplies with any element to give back the same element. And not only that, it commutes with any given element, including itself. What is the meaning of commutes? I think you understand the meaning of commutes, right? You can interchange. So Ex equal to xc equal to x. So this is the presence of identity. The identity is like 1 for multiplication, and multiplication what is relevant here. Okay. If you are talking about addition, it has to be 0. Okay, but here what is relevant is multiplication. Now go back to C3b. Does C3b have an identity element? Yeah. What is that? E or C1, whatever you want to put it. Doing nothing. That is the identity element. Fine. Third property, as you said correctly, is associativity. Right? It does not matter whether I perform BC and then A, or whether C and then AB. Doesn't matter. You get the same result. Now you have constructed the multiplication table of C3b notionally. From there, try and convince yourself that associativity holds. It holds. Right? Last, as Dola said correctly, is the presence of a reciprocal. Reciprocal means you have for every element R, you have another element S, so that Rs is equal to E. So you call S R inverse. Okay. Just don't forget that here we are not really talking about multiplication, division, division. When we write multiplication, for in our case for symmetry operations, for example, all it means is successive operations. Okay. Now going back to C3b, what is the inverse of C3? C3 square, do you agree? C3, inverse of C3 is C3 square. What is the inverse of sigma A? Sigma A. Sigma B is sigma B, like that. Alright. So you see, with the example of C3b, what we have done is, we have demonstrated, we have convinced ourselves that the symmetry operations of a given symmetry point group actually form a group. So, we can use group theory on the symmetry operations. Of course, it will be difficult if you want to keep on turning things, and how will you use group theory on that? That is why we need the matrices. Fine. But before that, let us remind ourselves of what is a cyclic group. A cyclic group, what is a cyclic group? And I have written abelian as saying cyclic, that is a different issue. A cyclic group is something in which the elements are like E, then maybe X, then X square, and so on and so forth. Okay. Cyclic group means, say take for example the C3 point group. If there is a C3 point group, what are the symmetry operations present there? E, then C3, then C3 square. Okay, there is nothing else. So, ABC, C is just B square. Okay, so that is what a cyclic operation, isn't it? That is a cyclic group. And in a cyclic group, what happens is that a cyclic group is also an abelian group. Abelian group means commutativity holds. AB is equal to BA. And one common confusion that we have is that we assume that associativity as well as commutativity holds for all groups. That is not correct. That is not correct. It may or may not be commutative. Okay. In cyclic groups, however, cyclic groups are abelian, and this commutativity AB equal to BA holds for cyclic groups. Alright. Fine. Group multiplication tables, we have already demonstrated what is group multiplication table using C3V, but let us now do a little bit of formal introduction to group multiplication tables. Okay. And we are on the last slide, I think. We are almost done, maybe second last. So, like C3V, what we can do is we can work with abstract groups. C3V is a very tangible group, isn't it? You know exactly what is the meaning of C3, you know what is the meaning of sigma V, right? But even before that, see, what we are doing now is that we have the benefit of hindsight. We know already that group theory holds and all that. But then when abstract group theory was formulated, nobody even thought that there is going to be an application in chemistry and all. So, it is completely abstract, it is just people kind of went with the flow and saw what comes out. So, let us retrace the paths of those pioneers, and let us see how we can work out the group multiplication tables of even abstract groups without knowing what is the meaning of A, B, C, etc. Okay. So, H equal to 1, that is kind of a moronic proof, right? Because there is only one, she says yes, moronic proof. So, there is only one element. What is that one element? E, not C, E. So, what would the multiplication table look like? We call it G1. You know about G8 and G10 and not G10, G8, G20 and all that, groups of powerful nations, and sometimes group of powerless nations also get together and call themselves G whatever, GN. So, that idea perhaps came from group theory, because we call them G1, G2, G3, G4 depending on what H is. So, G1 is kind of a stupid group, because only one element is there, that is E. So, if you want to write the multiplication table, you write E, E and E. Okay. If this comes in the exam, everybody gets 100 out of 100 and goes home happy. Okay. But fortunately, life is not that boring. So, let us go a little further. Let us talk about H equal to 2. H equal to 2, what is the name? G2, you got it right, G2. Okay. For G2, let us say that we have two elements, not let us say, if G2, if it is G2, it has to have two elements. What is the first one? E. And second one, because it is my initial, it should be A, right, EA. Let us try to write the multiplication table now, this is how I will write it. So, now see, what will be at the cross section of E and E? E, 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 simple. In fact, you can write the first line, EA, right. What will be E multiplied by A? It will be A. And what is A multiplied by E? Again A. Only one element is left, and you know, so what will this element be? My second initial D. You wrote A, so why don't you write D and complete the story? Because if you do, then you are going to violate this property of closure, right? Closure has to be there, so you better write E. Don't write anything else. And in fact, A into A is E. Not only closure. Why is it E? First of all, closure. Secondly, your inverse has to be there, right? So A has to be the inverse of itself. That is what we learned. For a group of order H, G2, A has to be inverse of itself. The sport chart doesn't have anybody else, right? So it has to be inverse of itself. Alright, Meher? Agree? Simple. H equal to 3. It's H3, so you should give the answer. It is just, yeah, EAB. EAB, G3, whatever it is, G2, that is a genuine mistake, not one made to. So this is the peril of copy paste. Even this has a moral in it. This is the peril of copy paste. When you copy paste, sometimes you paste and then you forget to replace. It is G3, of course, not G2. Okay, what will be the first row? Simple. What will be the first column? Now we have to work out the rest. What do I write? Do I write A or do I write B? Two options. %50 probability A, 50% probability B. What do we write? Now there is no probability. Probability of one is 1, probability of the other is 0. Because there is something called rearrangement theorem. Okay? Rearrangement theorem says that each row and each column lists each group element, too many eaches, once and only once. You cannot have an element that is missing in a row. You cannot have an element missing in a column. You cannot have a row or column which does not have an element. Have you understood the meaning? Okay. So what it implies is that no two rows or columns can be identical, right? Because if it's identical, if there are two identical rows, then what will happen? You go down the column, you will have the same thing twice. That is not done. No two rows or columns can be identical. Okay. Does that remind you of something? Yes, it does actually. I was going to say that. But does that remind you of something more related to physical chemistry? Or mathematics? We are talking about matrices. So what is the first cousin of matrix? What happens when in a determinant two rows are the same or two columns are same? 0. Right? Yeah. Fine. So what this implies is that each row and each column is a rearranged list of elements, and hence this interesting name of rearrangement theorem. Okay. Each row and each column is a rearranged list of elements. To understand where we are going, we can actually work out the different permutations. Okay. First column in any case is defined, and then we can work out the permutations in a way that no element is repeated in any row or any column, and we can actually construct the entire character table without even knowing what is the meaning of these elements A, B. Okay. So that is now how powerful abstract group theory is getting. Okay. Now, of course, is this word of God written on stone in letters of fire? No. So there has to be some proof or demonstration or something, right? What was words of God written on stone in words of fire? The 10 commandments. Here there is no commandment, right? So there would better be some proof. And this is how we can see that what we are saying makes sense. What is the nth row? Think of any group. Think of any general row, nth row. These will be the elements there, right? EAN, A2AN, so on. So A2 means the second one. First one is A1. It's just that we know that it is going to be E, so we have written E. Okay. So do you agree with me that this is what the nth row is going to contain? EAN, then A2AN, A3AN, so on and so forth, ANAN, finally AHAN, where H is the order. Make sense? Just close your eyes and think what it will look like. Make sense? Everybody convinced? I am not convinced that everybody is convinced. How do I write the elements there? What do I write first? The one on the top or one on the left? One on the top, right? So what is the second element on top? A2. And what is the element on the left? AN. So I write A2AN. Okay. Next one, what is it? A3 on the top. On the left, it is still AN. I am going from left to right in a row. So it is A3AN. So on and so forth. Finally, you are going to reach N there also. So it is going to be ANAN. And then last one will be AH, the last one, last element. And the second one will be AN. AN is always the second one, right? This is what it is. Now, what have we said? What does closure require? That these are all elements of the group. Okay. Now, are any two of these elements identical? See, everything is different, right? A1, A2, A3, A4, we have considered everything to be different, right? And that each of them multiplied by n, so they are all different. So no two elements are identical. That is the proof. Okay, that is the proof of rearrangement theorem. And incidentally, rearrangement theorem is discussed everywhere. I am following the treatment of cotton. That's all. But it is there in all the books that we have on our text. Fine. Now, knowing that, okay. So each entry in the row is unique. We already said that. Knowing this, what will now? Can you fill in the blanks? Can you do this Sudoku? What will this be? B. And what is this then? E. What is this? E. What is this? A. B. E. E. A. Right? So, what turns out here is that A is the inverse of B, B is the inverse of A. Okay? This is G3. And do you notice something strange here? Not strange maybe, but something unique here. Abelian group. Abelian group. It's also cyclic group. Cyclic or abelian group. Right? So, we stop here today and tomorrow we start at what? 5:30? 5:30. We start at 5:30 tomorrow and we start with this. We have gone up to h equal to 3. So, next we will go to h equal to 4. Okay. And meanwhile, what you could do is, okay, how many are there in C3? C3V, how many elements are there? 6. That's too large. You have to think of a group which is G3 or G4. What we will do is, we will compare the multiplication table of some point group which is either G3 or G4 and we will see we get the same thing. Alright. So, until 5:30 tomorrow.